Hi, welcome to the video on CPU scheduling. In this video, we are going to discuss the CPU scheduling, why we need to schedule a CPU. First, we see what is a CPU scheduling. CPU scheduling is nothing but picking up a process from the ready state, because in ready state there are many processes. Picking one of them and giving it to the CPU is called CPU scheduling. Then who will do that? The short-term scheduler will do it. A short-term scheduler along with a dispatcher. Sometimes dispatcher is a part of short-term scheduler, and sometimes they can be in different modules. The dispatcher modules give control of CPU to the processes selected by short-term scheduler. This involves context switching, switching to user mode, or jumping to the proper location in the user program to restart that program. Thus, dispatcher should be as fast as possible, whereas the scheduler are specially programmed system software which handle process scheduling in various ways. Then when it will be done, there are various cases when the CPU scheduling is done. So in first case, CPU is free and it can get some other process. It is a natural event, so it happens a lot of time. Whenever you give a process to the CPU, it gets executed and then we can pick up the next one. The first case is when a process switches from running state to waiting state. When a process switches from running state to wait state means a process is in running. It might need the IO or some other event or resource which is not currently available to it, and it is going to wait, or block in which it is going to wait for that particular resource. And at that time we can pick one of the process from the ready queue and we can schedule it. The second is when a process switches from running state to ready state. When a process switches from running to ready, a process could go from run to ready by. Why do you think that a process go for run to ready? There are two ways. One is a timer, or sometimes called time quantum. If you set a time for a process, then it will use that much of time and then it will leave the CPU. So the process will trigger a timeout event and move from running state to ready state. Or second case may happen depending upon priorities. Also it will happen. So how does it happen? Because of priorities. Whenever a new process joins the ready queue and it has the higher priority compared to the other processes, then this could happen. Alright. If already existing process has less priority and suddenly a new process who got created and has higher priority, then obviously we should pull out the less priority process and give the CPU to the higher priority process. The third is when a process switches from waiting state to ready state. If a process has done a transition from waiting to ready state, sometime what happen is higher priority process will go and wait for a resource or for IO operation, and it will wait in the ready queue in waiting state. And what happen is at that point the CPU becomes idle, and therefore you have to schedule the next process which is having some priority. Then later if the process which originally was in the waiting queue in wait state is now ready to execute and which is having higher priority. And the fourth is from running to termination. Whenever a process moves from running to termination, it means that a process which we have given the CPU is terminated and it does not need CPU anymore. So whenever the CPU is idle, we have to schedule it. So this is how scheduling works. Then we have a queuing diagram representation of process scheduling. There are various queues in CPU scheduling where the processes wait for their time. The first is, okay, you can see in this diagram the ready queue which contains the processes that are ready to be executed and submitted to the CPU. The processes are in ready queue and will be submitted to the CPU. Next, you can see that when an IO request is generated, the process is moved to the device queue. Here, the device queue. For IO operation. Then IO operation is performed and after that the process is sent back to the ready queue. IO operation is performed and sent back to the ready queue. Another is the time quantum. Similarly, when the time quantum of a particular process expired, the process is pulled back in the waiting state. Here time slash is expired, pulled back in the waiting state, and when the timer is over, the process will again sent to the ready queue. Here there is the third queue. When child process is created, the process have to wait for its child process to be completed. When the child process execute and completed, then the result is transferred to the parent process. Then the process again put in the ready queue for further execution. And the fourth queue is when an interrupt is generated. At last, you can see when a process is executing and an interrupt is generated, the process waits for that interrupt and again move to the ready queue. Here interrupt occur, move to the ready queue. So this is a queuing diagram representation of a particular process scheduling. Then we come up to the performance metrics for CPU scheduling. Now let's take a look on the performance metrics or criteria that are used in CPU scheduling. The first criteria is used CPU utilization. We want to keep CPU as busy as possible. CPU utilization may range from 0 to 100%. So the percentage of time that CPU is busy is called CPU utilization. The second is the throughput. The number of processes completed per unit time is called throughput. If the CPU is busy executing processes, then work is being done. One measurement of work is the number of processes that are completed per unit time is called throughput. The third criteria is turnaround time. From the point of view of particular process, the important criteria is how long it takes to execute that process. So the interval of the time of submission of a process to the time of completion, this time duration is called turnaround time. Fourth is waiting time. The CPU scheduling algorithm does not affect the amount of time during which the process executes or does an IO. It affects only the amount of time that a process spends waiting. So the sum of the periods spent waiting in the ready queue is called waiting time. Fifth is response time. That in the time of submission to the time the first response is produced is called response time, because in an interactive system turnaround time may not be the best criteria. Often a process can produce some output fairly early and can continue computing new results while previous results are being output to the user. Thus, another measure is the time from the submission of a request until the first response is produced. It is called response time. Then we come to the goals of CPU scheduling. The primary goals of CPU scheduling is to maximize the CPU utilization. We have to utilize the CPU as much as possible. The throughput maximization, maximum throughput generate, fairness, all processes gets executed fairly, minimize the turnaround time, amount of time in which the process gets completed, we have to minimize it, waiting time, the amount of time a process waits, and response time, process time take to response to the system is called response time. We have to minimize it. Then methods of evaluating CPU scheduling. So there are various methods for evaluating scheduling algorithm. First is by simulation. In this, simulator gets the workload from the system and then selects one of the scheduling algorithm and simulate the conditions. The performance is computed based on the results obtained from the simulation result. This method is the best for all as it gets the real-time workload from the system and then simulate it with the algorithm. Second method is queuing model. In this model, the behavior of queue is analyzed under some assumptions. This method needs a lot of mathematical calculations and it may not be accurate because it uses some of the unrealistic assumptions. And the third is deterministic modeling. Alright, in this model we take a predetermined workload and run the algorithm manually. Based on the algorithm used, we calculate the performance metric. It is not considered the best model, but it can give a lot of insight about the scheduling algorithm. All we need is the parameter and workload. So let's take an example. Suppose we have three processes A, B and C submitted at time 0. So arrival time of all the three processes is 0. Next is that we want to know response time, waiting time and turnaround time of process A. Let's assume that processes are executed in order they arrive at time 0. So process A gets executed first, so the response time of A is 0. Waiting time is the amount of time it waits for its execution. You can see when A waits, when process B and C executing, so waiting time is 2 plus 2 and 1, total 5 unit time. Turnaround time is the amount of time a process take to get finally executed. So A arrives here and completed here, so this is the total time taken to execute the process A is called turnaround time is total 9. Wait time, A started executing here, then wait for this and this much amount of time, then finally A appears, then wait this and this much time, then A execute, then remaining C and A. So A wait for 2, 2 and 1, total 5 unit of time. Now we want to know the response time, waiting time and turnaround time of process B. The response time of process B is 1 unit time because B gets first appear in the chart after execution of A. The waiting time of B is the amount of time B wait in the ready queue, 1 unit. Then 1 1 2, 2 plus 1, total 3 unit of time B is waiting in the ready queue. Turnaround time, the time it takes to execute fully process D, this is 3 plus 2, 5 unit of time. You can see 1 2 3 4 and 5. So the turnaround time for process D is 5. Then the same parameter for process C, the response time of C, you can see clearly, is 2 time interval or 2 unit time. Waiting time for C is 2 plus 2 plus 1 plus 1. So 2 plus 2 4 and 2 6 unit time. Turnaround time for process C is 3 plus 3 plus 3 and 1, total 10 unit of time. So next we move on the versions of scheduling. First is preemptive and second is non-preemptive. Many CPU scheduling algorithms have both preemptive and non-preemptive versions. In preemptive scheduling, we schedule a new process even when the current process does not intend to give up the CPU. This happens due to arrival of a process which has higher priority than the current process, or when the process which arrives has less execution time than the currently running process, then we can preempt the currently running process and execute the new real life process. And second is non-preemptive. In non-preemptive scheduling, only we can schedule a new process when the current one does not want to execute or does not want to use the CPU anymore. So whenever the current process is executed and it does not want to use the CPU, or it is going for some IO operation, we can perform the other process to execute. Now we will not preempt it forcefully. The CPU scheduling policies. So here we discuss some algorithms of CPU scheduling. First is first come first serve, second is round robin, third is shortest job first, fourth is priority, fifth is multi-level feedback queue scheduling, and there are many more algorithms like lottery scheduling which can be implemented in our policies. So let's take a look on first come first serve. As the name suggests, the process which arrives first will be executed first. Assigns the CPU based on the order of the request. The CPU will be allocated to a process in order which they arrive in the ready queue. It is a non-preemptive scheduling. A processor keeps running on CPU until it is forcefully blocked or terminated successfully. It is also known as FIFO scheduling, means first in first out. It is simple, but the drawback of first come first serve scheduling is a short job can get stuck behind long job. If a very long job begins to execute, then a shorter job may have to wait for a large amount of time for its turn to be executed. Second is round robin scheduling. In round robin scheduling, we assign a time quantum for each process, periodically release the CPU from long running jobs. Based on the timers or time quantum, the interrupt is generated, so short jobs can get a fair chance of getting executed or getting the CPU time. It is preemptive, when a process can be forced to leave its running state and send it to the waiting state, and we can replace it by some other process. And other is the time slice. The time slice depend on the use of the process, what interval we want to assign to that particular process. So here is some more topics about the round robin. If time slice is too long, the scheduling degrades to FCFS. If we take the time quantum very large, then it increases to tend towards the first come first serve scheduling. If time slice is too short, then context switching will occur frequently and throughput also suffers from it. Context switching is from switching from one process to other processes, saving the current state of the process and loading the other process is called context switching. So context switching from one process to another process increases. This is the drawback of round robin scheduling when the time slice we consider is too short. Then first come first serve versus round robin scheduling. Here the turnaround time of A, you can see turnaround time of B and turnaround time of C. In round robin, the turnaround time of particular process may increase, but they get a fair chance to be executed. Response time here you can see is very less than the first come first serve scheduling. In first come first serve scheduling, turnaround time of process A, you can see turnaround time of B and turnaround time of C. Turnaround time of C is same in both the round robin scheduling and first come first serve scheduling, but the turnaround time of B and A decreases, but the response time, you can see response time is larger in first come first serve scheduling. Next is shortest job first. The job which has shortest CPU cycle will be allocated first. So SJF runs whatever jobs put the least demand on CPU, also known as shortest time to completion first. Probably optimal in terms of turnaround time, maybe the turnaround time gets decreased due to this shortest job first scheduling, as the processes which have shorter job get executed first and the processes which has large CPU time will be executed thereafter. Great for short jobs, and the advantage is the short job does not have to wait for a large amount of time. The small degradation for long jobs. When the short job gets executed, then the long jobs gets CPU cycle. SGF illustration: response time of A is 0, response time of B is suppose 2 unit time, response time of C suppose 5 unit interval of time. Here you can see waiting time. Shorter job, A is shorter than B, B is shorter than C, C is largest, so largest job executed thereafter. So here the response time, you can see, is minimized and waiting time for these small processes also gets minimized. This is the advantage of shortest job scheduling. Here is the turnaround time. Turnaround time is the amount of time process take to get finally executed. You can see the A, a smaller process, get executed first, B, larger than A thereafter, and then C. Shortest remaining time first. A preemptive version of shortest job first is called shortest remaining time first. If a job arrives with a shorter time in the ready queue, then the currently running process is preempt and the shorter process gets executed. It is also known as shortest remaining time to completion first, generally used as the base case for comparison. It is a preemptive SJF scheduling based on the remaining time of a particular process. The drawback of shortest job first scheduling is starvation. Constant arrivals of short jobs can keep long one from running away. When we are using preemptive SJF and short jobs are keeps arriving in the ready queue, then the large processes will not get a chance to be executed because they will be preempted all the time. There is no way to know the completion time of job most of the time, because we do not have a predetermined completion time most of the time of a particular process. Then we move on to the priority scheduling. The process with the highest priority runs first, as you can see in the diagram. Priority 0 for process C, priority 1 for process A, priority 2 for process B. Let's assume that the lower number has the highest priority. So the C has highest priority, A thereafter and B thereafter. So the C gets executed first, then B, and then A, and then after B. Priority 0, priority 1 and priority 2. In this order they will get executed. The next is multi-level feedback queue scheduling. In this scheduling, there are multiple levels of queues based on time quantum, and they are fed back with the processes. So as you can see, this uses multiple queues with the different priorities and different time quantums. The round robin at each priority level is executed. First you can see we have a queue with a time quantum 8 with the higher level of priority. When a process having less than 8 unit time will get executed first. If it remains, then it will be fed back to the time quantum 16 queue in the lower level. Then most of the processes will get executed, as it will take 16 plus 8, total 24 amount of time they will be get executed here. And when they are not able to execute, then we can feed back into the lower level queue, that is first come first serve. So here in order execution will be done. The process which arrives first will be executed first. So in this manner we can achieve a multi-level feedback queue scheduling. Here various algorithms can be implemented in various levels of scheduling based on the applications of the user. So here is the summary. First come first serve, simple but cause short job to wait for long jobs. If we execute long job first, or suppose if a long job arrives first, then shorter job have to wait. There is no other way to execute. Then shortest job first, it is optimal, but need to know the length of next burst. We can only execute it when we know the next process takes how much amount of time, so that we can use. Round robin is used when we have to decrease the response time, or we have to allocate the CPU fairly among the all processes to decrease the response time in responsive systems. Then multiple queue use the best of each algorithm by having more than one queue. As you can see, we have discussed earlier multi-level queue scheduling. The algorithms which are best can be implemented at multiple levels of queue. That's all from my side. This lectures give a brief introduction about the CPU scheduling. Thank you.